I will talk in English. I'm sorry, my French is not extremely good, so I'll try not to talk extremely fast, like I sometimes naturally do. So first of all, can you hear? Is this loud enough? Okay. So I'm working. So I'm a computer science professor at the University of Utah, but this year I'm on sabbatical and working for Benjamin's company, and I want to talk to you a little bit about one of the things that I've worked on while I've been here in Paris. So as we all know, one of the really hard things is finding the border between feasible states and infeasible states of a computer program or a computer system. Any state that's feasible is reachable by some execution, and any state that's infeasible is not reachable. And the border between these is extremely difficult to discern. Testing explores the feasible region. Formal verification attempts to bound the infeasible, or to conservatively bound the feasible region. And figuring out whether a particular state that's near the border is really extremely difficult. And a lot of our problems in computer science and in information assurance come down to trying to more precisely determine what states of a system are feasible. So of course there's some initial state that the system starts in, and then of course any state in a feasible region can be executed by some actual execution, and no execution reaches the other states. So as I said, this is sort of extremely hard in practice, and you know, almost all of our work on formal verification and testing is just trying to answer this simple question about whether particular states of computer programs are feasible. So one of the things we can do is using either explicit specifications, like we saw some examples of this morning. Explicit specifications about program behavior, or using implicit specifications that come from programming language definitions. So using some kind of specification, we can define erroneous states for a computer system. And then we sort of want to, what we want to know is whether these intersect, whether some erroneous state is feasible. And if any erroneous state is feasible, then the system has hit a bug, and of course we have a problem. When we do formal verification, we over-approximate the set of feasible states. That is, we compute a larger set of states, which includes all of the feasible states of the system, plus also, usually at least, some infeasible states. So we over-approximate, and we're forced to over-approximate because the exact shape of the feasible state space of the system is too complicated and too difficult to characterize precisely. We don't know how to do that, so we over-approximate. And then, of course, we can catch all of the bugs in the system, but we also have generally some spurious intersections between the over-approximated state space and the set of erroneous states. And we get then false alarms, and we have to not necessarily waste time, but spend time dispatching these false alarms, spend time proving to ourselves that these alarms here aren't actually feasible, even though the over-approximated version of the state space makes it look like they are feasible. So testing, on the other hand, works differently. It starts from the initial state of the system, and it only proceeds to feasible states. So testing does not run into the false alarm problem. It explores more and more states, and of course it's going to miss some states, so it can't guarantee the absence of errors, but at least it's not going to force us to waste time on false positives, on false alarms, I should say. So of course testing might eventually find the bug, or of course it might not. So testing can be unsatisfying, at least from a computer scientist point of view, because it gives no guarantees. When we test, we sort of might eventually feel good about ourselves because we've spent maybe 2 years testing or something, but we still don't have any guarantees. And you know, as a consequence, real software systems, routinely ship with bugs, and their bugs are often very severe, and they often cause amazingly incredible security vulnerabilities on the internet. And it's sort of very poor. It's a very poor situation that we find ourselves in the world. It's a sort of I would say almost ongoing disaster in computer security. It's really very bad, really very bad these days. So of course we like to do verification. Formal verification is extremely nice. That's an extremely attractive idea because it allows us to possibly avoid parts of this computer security nightmare by guaranteeing the absence of bugs. But the problem is that real software has so many bugs that while we're guaranteeing the absence of bugs, we're going to run into a lot of real bugs. And that's not very fun. So if you have a system where you might be getting some false alarms and you mix in with those false alarms a very large number of true alarms because real software is really buggy, then the formal verification exercise becomes really maybe not very fun at all. Does that sort of make sense? The formal verification of a system that isn't actually correct is quite unpleasant. So that's the situation we find ourselves in. So if we're doing formal verification of, for example, an avionics piece of avionics software where we're really almost sure already that it's correct, then formal verification can sort of proceed naturally. If we apply formal verification technology to something like maybe OpenSSL, it's going to be extremely difficult because of the incredibly big number of real bugs that we're going to run into, in addition to any false alarms that might be signaled by our tool. So one of the things that we've been working on at TrustInSoft is trying to bridge the gap between testing and verification by, so you probably know Framesi mostly as a static analysis tool, as a formal verification tool, and of course that's its primary purpose. But one of the things that that Pascal at TrustInSoft did is came up with a mode of using Framesi as an interpreter, so as a C interpreter. So now it concretely executes the program instead of abstractly executing the program, and a concrete execution of a program is not going to have any false alarms. So this is of course a big advantage when we are trying to attack a big piece of software which actually has bugs, plenty of real bugs in it. Now on the other hand, of course, once we're using an interpreter instead of a pessimistic static analyzer, now of course we are going to miss bugs, but what we can hope to do is, by combining the interpreter approach with very good test case generation approaches, we can hope to find most of the bugs using the interpretation approach, and then when we finally change modes and do static analysis, we can attack a piece of software where most of the actual bugs are gone, and then the verification effort can proceed in the way that verification is supposed to proceed, where the effort goes towards proving the absence of bugs, not somehow mixing proving the absence of bugs and finding bugs. And again, real open source software really just does contain a lot of bugs. This is not sort of, I'm not sort of making up things. I mean, there really are, large numbers of defects mixed into open source software. And formal verification tools, sound static analysis tools, are obligated to report all of them because the entire goal is to prove the absence of bugs. And you can't do that until you've reported all the bugs. So this interpreter mode of Framesi, we'll call it TIS interpreter here, it's the TrustInSoft interpreter, is an interpreter for C, and the thing that makes it better than other C interpreters, like, Intel processors can be used as C interpreters, right? But the TIS interpreter does a very good job finding undefined behavior bugs. That is to say, finding violations of the language rules that C programs sort of routinely execute while they're running. So I'm mostly going to be talking here today about undefined behavior bugs. And so remember that there are these two classes of bugs we want to talk about. One is violating specifications written by humans. I'm not really going to be talking about that. We're going to be talking about violating the implicit specification imposed upon a C or C++ program, or of course a program in any other language, by the language standard. So when you write a program in C or C++, you're sort of agreeing not to do all of these things that you might want to do, like divide by zero, that violate the implicit specification handed to you by the language standard. And the problem with these languages is anytime you violate the rules, the language doesn't tell you generally, and since the compiler assumes that you don't do these things, the consequences of violating the rules are generally severe. And one of the common consequences of undefined behavior in C and C++ code is arbitrary remote code execution, right? So almost all stack smashing, buffer overflow kind of bugs that we know and love, or maybe know and hate, stem from undefined behaviors in C and C++. So The problem is that basically all real C and C++ programs contain these undefined behavior bugs. And like I say, so what I'm talking about today is using this interpreter-based approach to try to get rid of as many of these bugs as we can before we attack the program using, before we attempt formal verification on the program. And again, this is something we're sort of forced to do when we attack Unix applications and that kind of thing with formal verification because they just contain so many bugs. And we have to get rid of them somehow before we can even think about performing formal verification on them. So it's very different than attacking, you know, sort of some extremely tightly written embedded system code or something like that. So just to illustrate what I mean by undefined behavior, this program here, not this program, sorry, this function executes undefined behavior. The undefined behavior is that in C you're not, or C++ as well, you're not allowed to shift a number by greater than one less than the bit width of the value. Okay? And so if you shift a
in the overflow on the addition?
We'll ignore the overflow. The overflow might or might not. The addition might or might not overflow. Here we can't tell, but the shift always overflows. So the compiler, faced with an undefined behavior, actually has no obligations. So the standard explicitly says this. It says the compiler has no obligations when executing an undefined program. And if the program is always undefined, the compiler essentially really does lose all of its obligations. And so this is what we get from the most recent version of LLVM. So does that make sort of make sense? The function just returns. And the return value is whatever was sitting in the register which contains the return value, just whatever junk was sitting there. And the compiler didn't even bother to pretend to do the addition or the shift, because it didn't need to. So are we all clear now on the sort of one of the kinds of effects of undefined behavior bugs? The compiler loses its sense of obligation. And this is a correct C compiler emitting this code. This is not a buggy compiler. It's a correct C compiler. The compiler has lost its obligations and it goes ahead and just returns from the function. It didn't even have to, the compiler didn't even have to return from the function. But it was being kind today and decided to give us a return instruction. So we should feel lucky, possibly. Other similar programs and for other versions of LLVM don't always give you a return instruction. So as we know, most of the safety and security critical code in the world is written in C and C++. And undefined behavior has been a major problem in these programs. And undefined behaviors such as buffer overflow bugs have been responsible for a large fraction of computer security problems over the last 20 years. So if you go back to the Morris internet worm in the, what was it, in the 80s? I think 80s, 1988 is it? The first worm. This exploited undefined behaviors in for example, the finger daemon that was running on the Unix machines at the time. Okay, so the solution to undefined behavior problems is tools. So if you don't give programmers tools to solve undefined behavior problems, then they can't fix them. They can't find them. And the problem is that the issues, the undefined behavior bugs, are subtle enough that even, generally speaking at least, even very good programmers can't keep them out of their code. So again, the answer is to give people tools that detect undefined behaviors. And once you give people tools that can detect undefined behaviors, then they're capable of getting them out of their code, because we've basically reduced the problem to a test coverage problem. So if we have dynamic checking tools and we have test coverage, now we can largely eliminate undefined behaviors, at least in the parts of the system that we're able to test. And you would think that you should be able to test all of your code. And in many domains you'd be right, but for Unix applications that's absolutely not the case. So what he wanted to do here is show a sort of a Venn diagram of a subset of the undefined behaviors in C and C++, and I guess I'm focusing on C here. And I'm going to tell you about what is more or less the state of the art in detecting undefined behaviors in C and C++ programs using tools, using dynamic checking tools. So one very strong family of undefined behavior checking tools is represented by the left-hand white oval. And these are tools such as Address Sanitizer or Valgrind. So both of these are dynamic checking tools that instrument a program and run it on sort of an instrumented platform that detects out-of-bounds array references, use after freeze, and that kind of bug. So To a large extent, dynamic detection of memory-related undefined behavior bugs, this is more or less solved, as long as you don't mind your program running quite a bit more slowly. Another collection of undefined behavior bugs is found by an LLVM checker called Undefined Behavior Sanitizer. Undefined Behavior Sanitizer is it's essentially a flag you can pass to Clang, to the LLVM compiler, and in this detects integer overflows, divide by zero, alignment, memory access alignment problems. It detects sort of a large class of undefined behavior bugs that don't relate to memory out-of-bounds errors or use of uninitialized memory. There are other checkers available, but Valgrind, Address Sanitizer, and Undefined Behavior Sanitizer are sort of some of the best current dynamic undefined behavior detection tools. So a program like TIS-interpreter finds very nearly, at least, a superset of the problems found by the Undefined Behavior Sanitizer and Address Sanitizer. So there are some bugs that you can make, such as misuse of variadic functions in C, unsequenced accesses to variables, that is to say, increments or decrements or assignments or other modifications of variables where the order of the modification is indeterminate according to the language. That's undefined in C. Comparisons of pointers that are point to different allocated blocks of memory. In C and C++, if you use dynamic memory allocation to grab two memory objects and you have pointers into them, they can't be compared using equality or relational operators. And so these bugs, like the variable arguments bugs, unsequenced variable accesses, and comparisons of unrelated pointers, those aren't found by essentially any tool that exists except for TIS-interpreter, except for Framesi in the interpreter mode. Now there are also some undefined behaviors, and now I'm back to the outer white space here, that aren't detected by any tool that I know of, currently at least. So violations of C's strict aliasing rules are extremely difficult to avoid manually, and this is essentially unchecked by tools today. These bugs are very, very nasty and have broken a lot of real C code. Infinite loops that lack side effects and that don't have a constant controlling expression are undefined in C and C++. That's sort of a very weird and, to many people, unexpected undefined behavior. But the compiler likes to delete infinite loops if it can. And there are some technical reasons why that's a desirable thing to be able to do. And no tool detects those. No tool detects that problem that I know of so far. So there are a lot more undefined behaviors than the ones I've listed on the slide here, but these are kind of the ones that I think are the most important and the most interesting, and they're the ones that sort of, and I'm showing you how they kind of fit into the universe of available detection tools for these undefined behaviors. So one thing we've been doing at TrustInSoft is applying TIS-interpreter to some open source libraries that kind of sit at the security boundary of the internet. So things like image decoder tools, image decoder libraries, I should say, and cryptography libraries, these things sit there and process untrusted data from the internet. And if you ever mess up processing untrusted data from the internet, somebody will take over your computer. Does that make sense? Somebody will take over your computer if you erroneously process untrusted data. And so anytime there's a security-related bug in, for example, bzip or libjpeg, almost the entire internet becomes vulnerable as soon as it's discovered. Of course, almost the entire internet was vulnerable the whole time. But once the bug becomes discovered, it becomes not only vulnerable, but sort of actively vulnerable. So these are worthwhile libraries and programs to attack with sort of advanced tools. So when we use an interpreter-based approach to find bugs, the sort of advantage, as I said earlier, is we don't get any false alarms. The disadvantage is we need test cases, and the checking is only as good as the test cases. And what we've been doing to get test cases is more or less relying on a program called AFL-Fuzz. It's a sort of a modern coverage feedback-based file format fuzzer, and it's extremely strong at generating inputs that cause programs to execute into weird corners of their state space. And so combining this with the interpreter, that's a very sensitive undefined behavior detector, has led us to be able to find quite a few bugs. We'd find more bugs if we did full formal verification, full sound static analysis of these programs, but that's much harder than what we're doing. Does that kind of make sense? So we're sort of we're still looking for sort of easy bugs while we're on the way to deciding what it is that we might want to actually formally verify.
I've had first test case generator is doing static analysis to generate the cases or not at all?
It's not doing static analysis. What it does is it instruments the binary to look at where the test case executes. So when AFL monitors the execution on a test case and uses information about the coverage to try to cover more parts of the program. So it's not static analysis, it's dynamic analysis, but it generates the kind of things that you might generate with a static analysis-based test case generator. It's just doing something sort of easier because it doesn't have to use a solver or anything like that. So what I'm going to talk to you about a little bit today is SQLite. And so SQLite is an open source embedded database. And SQLite is a really an ubiquitous piece of software. It's you know, I don't know that it's the most widely deployed piece of software, but it's one of them. It's one of the 10 or 20 most widely deployed pieces of software, probably. So one way to think about it is almost every web browser contains a SQLite database embedded within it. Almost every operating system does, and even dumb phones. So of course, smartphones have probably many instances of SQLite hiding within them, but even dumb phones did. And the idea is that SQLite is unlike a traditional relational database manager. So traditionally, a relational database manager is a pretty heavyweight thing. It's a pretty big object to get running and set up, and it runs in a separate machine or a separate Unix process from the clients of the database. SQLite embeds within the process that's using it, and thereby avoids all the configuration hassle and a lot of the overhead of running a database. And so what SQLite basically did is it took a lot of data management problems that were difficult to solve and made them essentially trivial. You just include SQLite as a library in your application. So anyway, so this is an extremely widely deployed package. The SQLite author believes that it's at least has 10 billion instances in the world. So it's very widely deployed. So looking at this piece of software that's incredibly widely deployed seemed like a good idea to us because, first of all, it's big. It's probably too big for formal verification, at least within a short time frame. And it's really important that we find security problems in it. So this looked like a good target to investigate. So one of the nice things about SQLite is, unlike most open source programs, its maintainer and its developer is incredibly fanatical about testing. So most open source software, if you look at the test suite that comes when you type make check or whatever when you build the software, it's generally fairly poor. Is that, hopefully this sort of rings true for people. When you type make check, it runs a few dozen or a few hundred test cases, and the test case coverage is usually quite poor. SQLite is not like that. It's tested with many, many thousands of test cases, and the author has achieved 100% MC-DC test coverage, which means that every entry and exit point to every function is covered, so that's easy. Every decision inside the code takes every outcome, so now he's achieved 100% branch coverage. That's also not too big of a deal.
What's the Oracle?
Sorry?
What's the Oracle, the test Oracle? Because you can only detect as many bugs, and there's a lot on quality.
Well, he has a whole family of test oracles. One oracle he likes to use is he'll run the same query with and without query optimization. Another oracle we can use is Valgrind to look for, or TIS-interpreter, or something like that to look for undefined behaviors. So there's a wide variety of test oracles. Some of them domain specific, like checking that the results of a query are the same. Other ones non-domain specific, like the one we're using, TIS-interpreter, or something like Valgrind. So there are a lot of test oracles.
So 100% MC-DC coverage, it's just checking that the thing doesn't crash.
Well, no, I mean, each test case runs under whatever oracles he can make it work under. Like I say, a lot of them are run with turning on and off a particular optimization or changing the configuration of the database and making sure that the query has the same result in both cases. So the oracles are often good, and when he doesn't have a good one, he uses a bad one. Okay, so the second line there says that, he has achieved 100% branch coverage, but also 100% MC-DC coverage means that every condition inside a decision, that is to say every composite Boolean inside of a larger conditional, has to have both outcomes during testing, And finally, every condition in a decision, and a condition would be something like A is greater than B or something, has to be shown to independently affect the outcome of the overall conditional that it lies in. And so this is a level of testing that's seldom seen outside of domains like avionics. It's really, really serious. And he's really, this developer has put a really enormous amount of work into testing SQLite. And what that does is make SQLite an extremely good match for TIS interpreter, which needs a test suite which has really good coverage because it's this very fine-grained oracle for detecting undefined behaviors. So what we did is we got a hold of the test cases, and they're unfortunately, although the database is open source, the test suite isn't. But anyway, we got a hold of it. The developer gave us access to his internal really good test suite, and we started running them sequentially through TIS interpreter to try to find problems. And the idea is that he had already run SQLite and all of his test cases using all of the best available oracles before TIS interpreter. So he had run it using Valgrind and address sanitizer and undefined behavior sanitizer, all of the best. He had done all of the things that he could do without this tool that we had. So he had fixed all the bugs that were found. So the bugs that were left were ones not found by the sort of major available tools. So the question you could ask is, well, was there anything left to find? And of course there was. There's plenty of stuff left to find. And I'll tell you just a little bit about it now. Here's sort of a weird thing about C. So maybe only those of you in the audience who sort of enjoy C will sort of enjoy this bug, but I'll just talk about it quickly. You're not allowed to pass a null pointer argument to a function like memcopy. So memcopy copies a block of RAM from one location to another location, and normally you can't pass a null pointer to memcopy because then it would just crash the computer right away. But it turns out that when you're writing a loop that's copying data from one place to another, and you have a memcopy in the loop, very often the final iteration of the loop will pass a 0-byte argument, 0 bytes to copy, and a null pointer to memcopy. It just happens to be a useful idiom. It turns out that's undefined behavior in C. And furthermore, it's an undefined behavior that the compiler actually takes advantage of. So let's look at a program here where I have taken 2 pointers, P1 and P2. They've been passed to my function. Now I'm passing those 2 pointers to a memcopy call. So those pointers might be null or might not be null, right? They could be anything. And then if the first pointer was null, I'm going to call an error handler. And the compiler, GCC, optimizes this to just a pure jump to memcopy. And the idea is, the idea that the compiler has in its head is, if P1 was null, we shouldn't have called it in the first place. The behavior would be undefined by the C standard. Therefore, P1 isn't null, and the call to error handler is dead. And we just have a tail call to memcopy. Does that sort of make sense? So it's a very dangerous kind of optimization for the compiler to be performing, but these compilers, these modern day C and C++ compilers love dangerous optimizations. They just do this aggressively.
Sorry, I disagree because, I understand the point, but you told in the previous slide that the test cases went to all testers. So they should have put that.
I made up this code.
Okay. It's not okay.
This is an example to show what the compiler will do. Yeah. You're right though. You're right. Yeah.
I think that's a good point. How does the developer of SQLite, how can he be sure that he has full NCPC coverage if he only tests that with Valgrind on binary code?
You have to trust him a little bit. His test coverage infrastructure is test coverage infrastructure he wrote himself. You have to trust him. Or you could verify it using some other test coverage tool if you didn't believe him. But we just believed him. We didn't try to see if he was wrong about his claim of 100% coverage. So I know people who I have a friend who works in testing and who used to work at NASA doing testing, and he thinks that the SQLite test code is one of the best test suites he's ever seen, including avionics. So smart people who I trust think it is really good. Maybe there might be errors in what he did. It's a claim that he made that people haven't really tried to back up. Anyway, so he has this custom test infrastructure, test coverage infrastructure, which actually might only work on the assembly language. So in that case, if the compiler eliminated the conditional, he might actually miss that. In any case, this bug where where a null pointer is passed to memcopy and similar functions was found in SQLite. So you know, this is a bug that we found and reported to the SQLite developer. He didn't know that this bug had been there, and he had some things to fix. And like I say, the reason I show you this particular example, which I made up, is to show that it really is a dangerous undefined behavior to do, because it allows the compiler to derive something which may actually be false in an execution where the pointer is null, which he actually had in SQLite. So another kind of bug we found in SQLite were bugs in uses of variadic functions. So variadic functions, or variable argument functions in C, are functions which take, first of all, an argument that has a fixed type, and then they take almost anything. They can take, you can pass almost any sequence of arguments to one of these functions by essentially constructing a stack frame full of whatever you want, and then the callee then has to parse this stuff off the stack in an almost type-free manner. So C is already, even without variable arguments functions, a very weakly typed language, right? But this is the weakest by far of any part of an already really weakly typed language. This is you know, there is no safety net when you do this kind of stuff. You're just manually grabbing stuff off of the stack. So what we have is a function, a configuration function, SQLite 3 config, which takes a configuration command. Here I'm showing an example of this logging configuration command. And it also takes some other arguments which are, and the other arguments, the variable arguments, are specific to the configuration command. So he only wanted to write one configuration command, one configuration function, and it takes a whole bunch of different commands. And since the following arguments are dependent upon the command, it has to be a variable arguments function. Does that sort of make sense? So in this variable argument function, it parses, it dispatches based on the command that it's been given, and then it pops the rest of the pushed arguments off of the stack. So in the example here, the caller has pushed a null pointer onto the stack and a pointer to a function, and then those are popped off the stack as void pointers. So the issue is that this code is broken. And the reason that it's broken is because normally in C or C++, a zero constant is interpreted in a pointer context becomes a null pointer. But when we have basically a completely typeless environment, like the list of arguments being passed to a variable arguments function, the compiler doesn't know to interpret the zero as a null pointer. It just thinks it's a zero integer. And that can cause a real problem on a platform where an integer and a pointer are different sizes, because now we have mismatched data on the stack, mismatched stack frame in terms of actual bytes overlapping badly, and this could cause sort of really very nasty crashes. And yet it had gone undetected. And so the fix for this is to teach the compiler that the zero is a pointer, and not force the compiler to infer that the zero was a pointer, because the compiler just doesn't have the information. So this is the correct version of that code. And now the question is, why did this go undetected? Why wasn't this causing systems to crash? And it turns out that it didn't cause systems to crash for sort of a funny reason on different platforms. So on an x86 or on ARM32, on a 32-bit platform, the zero integer and a null pointer have the same size and happen to have the same representation. So it kind of happens to work. On a system like x86-64, where the integer has 32 bits and the pointer is 64 bits, this would be a very dangerous crash, where we have, essentially we're getting garbage memory and corrupting things, except that the x86-64 calling convention says that the first 6 scalar arguments go into registers, and when the 32-bit argument is loaded into a 64-bit register, it gets sort of an implicit promotion to 64 bits, and then it just sort of happens to work again anyway. So the sort of purest chance is the reason that this program works. And we found not only one instance of this bug, but like 30 or 40. I mean, this particular bug was scattered everywhere, because he wanted to pass null pointers to variable arguments functions, and none of them had casts. So on a platform where things don't happen to work out for the reasons I've described here, this would have caused memory corruption, it would have caused corrupted stack frames, and everything, the execution would have gone badly. So that's another kind of bug we found in SQLite. And like I say, there were dozens of this particular bug. And we hopefully found them all. Another kind of bug we found are uninitialized variable bugs. And the interesting thing was that we found uses of uninitialized variables even on code where Valgrind had been run on the code. And the reason that we found these bugs is because TrustInterpreter, and of course Framesi as well, looks only at the source code of a program. It's the model of the semantics for C is based on the source that it was given. On the other hand, a tool like Valgrind looks for uninitialized memory references by looking at the binary, by looking at the compiled code. And so in some cases, an optimizing compiler will cover up accesses to uninitialized memory in such a way that it can't be seen by looking at the binary. And one easy example of that would be, you could see that if the compiler did dead code elimination, then uses of uninitialized memory would go away in the compiled code. But it also can happen from stack frame reuse, where some particular part of the stack is initialized by one variable whose lifetime ends, and then it's used by a different variable that's uninitialized, but the variable was initialized by uses of the previous variable. Does that kind of make sense? Have I explained that well? Yeah. So Valgrind is essentially an unreliable undefined behavior detector because it only looks at the compiled code. And TrustInterpreter found some of these codes, including an uninitialized variable bug that was potentially really harmful, that was used by a sort of an important field. And the reason the code worked is a little bit obscure. The code worked because whatever previously used that memory seemed to have left a harmless value there. So that's not, of course, the reason we want our programs to work, is because something else happened to leave a value in memory that was friendly. But that's the reason SQLite was working until this bug got fixed. Okay, so let's look at a different kind of undefined behavior. So a pointer in C becomes illegal to use as soon as what the pointer points to goes away. So does that kind of make sense? So one thing C programmers really, really want to do is treat a pointer as sort of a value, a sequence of bits that doesn't change regardless of what happens to the memory being pointed to. And that view is nice, and it should work, and it would work in a language that was designed with common sense, but it doesn't work in C. In C, as soon as you free something, the pointer itself becomes indeterminate and illegal to use. So you can't even, for example, test a pointer for null after freeing what the pointer points to. That's actually illegal C code. And so that's what I've shown here. Here's an example where some storage was allocated, freed using a realloc call, and then a null check on the variable is performed, and that's undefined behavior. And we found quite a few instances of this bug in SQLite. And the reason is that in a long-running library like SQLite, the real enemy is, one of the real enemies is memory leaks. You do not want a long-lived library that's linked into your process to leak memory, because eventually it will kill your process. And so what the developer had done is generally tried to free memory as early as the memory could feasibly be freed. And in doing so, had freed things often quite a bit too early, because pointers to that memory were still used. The pointers weren't being dereferenced. So we didn't find any dereferences of dangling pointers, because any of those bugs that were in the code base would have been found by Valgrind or by Address Sanitizer or some other tool. But the uses of these pointers, which again is also illegal, are only caught by a more sensitive tool like TrustInterpreter. And like I say, we found a lot of these. And the reason seemed to be that the developer really tried hard to free the memory as soon as possible. So another kind of undefined behavior that's possible to do in C is taking a pointer to a block of storage and moving the pointer so that it points outside of the block of storage. So if we have an array of 10 integers, so A on the slide here, we're not allowed to construct a pointer to A sub minus 1. We're not allowed to point to the array cell before the array. We're allowed to, of course, make a pointer to the last element, to A sub 9. We're actually, through a special case in the standard, allowed to make a pointer to A sub 10. So that's not pointing to legal memory. We're allowed to construct the pointer to it, but we can't use the pointer. We can't dereference the pointer. And the reason that we're allowed to construct a pointer to A sub 10 is this appears in the last iteration of any loop that iterates over an array. All right, any pointer-based loop that iterates over an array is going to construct that pointer. So they had to add a special case in the standard making that legal. But it's not legal to point to a sub 11. So you can point to a sub 0 through 9 and then dereference the pointer. You can point to a sub 10 but not dereference it, and you can't point anywhere else. So that does that sort of make sense? So these are the sort of rules on pointer construction in C, and we found a bunch of places where SQLite constructed pointers that didn't fit these rules. So one thing we found is systematically creating pointers to the element before an array. And that was because there was a case in SQLite where, for some reason that I never really tried to figure out, he wanted to use one-based array indexing. He wanted to start his arrays at 1. But he didn't allocate an array and just index it starting at 1 because that would waste a piece of memory. He created the array, made the pointer point 1 before it, and now array sub 1 pointed to the 0th element. And so this is very clever, I suppose, but it's actually illegal C code. And this is one that so the SQLite developer fixed this because we showed him that was not.
It's illegal C code, but surely it's harmless, isn't it? So long as you don't redirect the pointer.
It's harmless if the compiler just doesn't decide to take advantage of it. The compilers have free license to take code like that and break it because it violates the standard. Some in undefined behaviors the compilers exploit and break the code. Other ones they don't. You know, it's one of these things where, but you're right. This one probably is harmless for probably mostly harmless for current compilers. But it's not necessarily clear that that's the case, but it probably is. So we found some systematic uses of invalid pointers, and also as part of input validation, it's often the case that there's an array of data received from the network, sort of an untyped array, and as part of validating that, you make a pointer point to various parts of the array, and it's really common in code that's doing input validation to index past the end of that array and do illegal pointer manipulation. And so this one is not at all harmless because the out-of-bound pointer can wrap around the address space, and then a bounds check for overflowing pointers doesn't trigger because the pointer points to before the array instead of after it. And that is actually a very harmful undefined behavior, and we found some of those as well. And that particular error is seen in most C code. So overall, we reported a bunch of bugs. I didn't keep exact score of the number of bugs, but number of dozens of bugs that were reported to the SQLite developer based on this work. And the developer fixed all of them that I reported because he really believes strongly in keeping a high quality code base. So he fixed all of these bugs. And then moreover, the main developer and his colleagues are hopefully at least more aware of some of these subtleties of the C standard. So a lot of people write C as if it's like 1992. And that kind of C that people wrote 20-some years ago just doesn't work any longer. It contains things that are undefined and also things that compilers exploit. And so a lot of people's understanding of C code hasn't sort of evolved to keep up with how hostile compilers are now. And so hopefully this work that we did had some indirect effects, in addition to getting the bugs fixed, to educating people about how modern C has to be written in order to make it actually work. So kind of in summary, the C language is full of these undefined behaviors. It's essentially impossible to avoid them without good tool support. It's almost impossible to avoid them without good tool support. And an TIS interpreter is, as far as I know, currently the most sensitive undefined behavior detector for C code that anybody has built. That is to say, it detects more undefined behaviors than any other tool. And so this is sort of a good thing to apply to important C codes. And then furthermore, using Framesi in an interpreter mode is a nice thing to do because it guarantees that the tool understands the code that you're running, which is good. You want to know that the tool can actually process the code before you launch a formal verification effort. And then the interpreter mode combined with good coverage should be able to eliminate almost all of the actual bugs in the code, at which point a formal verification effort is going to spend much less time on finding and reporting these bugs, and the formal verification effort can focus on what it's actually supposed to focus on, which is formal verification. And then TIS interpreter is open source, and you can grab it from the web page linked right here. Thank you.